Okay, we're going to do a quick recap of what's probably the most important law in all of electricity, which is Ohm's law. Now, I've got you to plot this graph now for an unknown resistor and then use the gradient to work out what the resistance is. And you all found, and most of you wrote up in your conclusion, that it gives you a nice straight line with very little deviation. And that's almost always true. Nice thing about electricity experiments is they're nice and reproducible. You get very little scatter, you get the straight line that you're intending, and you should have spotted that that straight line is going to go through the origin, making it proportional. Now from maths, you could say y is equal to mx. There's no plus c because it's going through the origin. So m is our gradient. And as you noted, that is our resistance. And forward direction, reverse direction, the same in reverse. So that's true for all resistors. Therefore, brings us to Ohm's law, which was first set out by Ohm in 1827, and he said that the electromotive force acting between the extremities of any part of a circuit is the product of the strength of the current and the resistance of that part of the circuit, which is a bit of a mouthful. We still use the term electromotive force when we say electromotive force, or we more normally write it as EMF. What we mean is the PD of the supply. So that term does comes up in the GCSE. So essentially it says the driving PD is equal to the current multiplied by the resistance, because product is just the Bosch maths word for multiply. So the driving potential difference of their circuit is given by the strength of the current multiplied by the resistance of the circuit, which we can write as V equals IR. We could have got there from our graph, because our graph showed that V was proportional to I, because it was a straight line graph that went through the origin. And in maths, you know that if you want to get rid of the proportional sign, you put in a constant proportionality. And the constant proportionality in this case is resistance. Doesn't matter whether I write IR or RI. A multiplication is commutative. It's the same either way around. 3 times 2 is exactly the same as 2 times 3. But it's normally written as V equals IR. So the only slight wrinkle in thinking about the graphs and thinking about V being proportional to I is that normally, actually, traditionally, what's called an IV characteristic, you thought me writing on a board was bad, you want to see, and now you can see me writing on a on an interactive laptop screen. Not great, but this is an IV characteristic. So the IV characteristic for a resistor is a straight line going through the origin, but for an IV characteristic, normally I's first, and the thing that's first is the thing that's on the y-axis. And so when we normally draw IV characteristics, we draw the current on the y-axis and the potential difference on the x-axis. Of course, that's the other way around to the way I asked you to draw it. And the reason I asked you to draw it what is effectively the wrong way around is that then when you do the gradient, you're doing V divided by, the potential difference divided by the current, which gives you the resistance. Whereas when you do the gradient this time, you've got the current, which is your rise, divided by the potential difference, which is your run. And so the gradient of this graph will be 1 over R. So actually what's going on here in terms of proportionality for this particular diagram for the IV characteristic is that we're saying that I, oops, wrong colour, sorry, I is proportional to V, and when we put in our constant of proportionality, I is equal to 1 over R times V. Now 1 over R does actually mean something. It's called conductance. So 1 over R equals conductance, and that has a symbol G. So I could say that I was equal to GV. And Ohm's law could have been written that way around. It's just that isn't the way around that Ohm decided to write it. Ohm decided to write it the other way around, and so we have Ohm's law with resistance instead of this law with conductance, which I have to say is an extremely good thing for me as a physics teacher, because the units for conductance are Siemens, and there's only so much giggling from year 9 I can tolerate. So we don't use it that way around, although we could, but we still draw the IV characteristic with the current on the y-axis and not the potential difference on the y-axis, which is what I asked you to do. So if that confuses you when you're having a look at graphs, you just have to bear that in mind. Now, the key thing here is it's a straight line. So the IV characteristic of a resistor is a straight line. And that means because the gradient is constant. If you've got a curve, gradient's changing. And because gradient and resistance are effectively the same thing, here, that means great constant resistance. Now a resistor, a conductor, like a bit of wire, they have constant resistance. So they give us a straight line IV characteristic. Not everything does. Over the next couple of lessons, we're going to look at a couple of things that do not have straight line IV characteristics and therefore do not have constant resistance. And we can still use Ohm's law. We can still say V equals IR, but that R will be different all the way along the curve. But for those things where the IV characteristic is straight, we call those ohmic devices. So a resistor is an ohmic device, and that's a bit of terminology you just have to learn. If it's got a straight line IV characteristic, then it is an ohmic device. Its resistance is the same, pretty much whatever we do to it. Now, when pinching things off the internet, you're not until you get them drawn out big do you always see how good or otherwise they are. The person who drew this one actually got it wrong. Resistance graphs do not bend halfway the way that this one does. So goodness knows what was going on that he's got that one bending. Crazy. What should be happening here is that one should carry on straight up there, and that one should carry on along there. So don't know who drew this, but they went a bit mad. Anyway, the reason I wanted to put this graph in anyway is for the fact that it illustrates for us the fact that with current on the y-axis and potential difference on the x-axis, the slopes go the opposite way from the way you would expect. In other words, the ones with the steepest slope have the lowest R. So here our resistance is increasing in that direction. So this one is the 4/10 of an ohm. 4/10 of course is 0.4. This one is 1 ohm, because you can see 10 amps, 10 volts, 1 ohm. This one is 2 ohms, and this final one that's been sort of badly drawn on here looks like it's got, for 10 volts, it's got 1 amp. I don't know what I was drawing there. Should be a 1, shouldn't it? For 10 volts, it's got 1 amp, and that makes that a 10 ohm resistor. Okay, so the point I'm trying to make is that you've got to watch out when you're doing exam questions, which way around your current and your voltage axis are. If it's a proper IV characteristic graph, the I will be the y-axis, and if the I is the y-axis, then resistance is going the opposite way to the way you would think it does. Resistance is increasing in that direction with a lower slope of the graph, because resistance is 1 over the gradient of the graph. Hope that makes sense. Okay, resistance. It's the constant proportionality linking current and PD. It's a measure of how hard it is to get the current to flow through a circuit, how much push, how much potential difference is necessary. In a formula, it's denoted by a capital R. And the unit for resistance is the ohm, named after George Ohm, who first discovered it. He was a teacher, by the way, when he discovered it, so he was obviously a very fine chap. And the unit is the Greek letter omega, because omega sounds a bit like ohm, so therefore we use the Greek letter omega for its unit. And like other SI units, we can use multipliers on the top. It's not at all unusual to come across questions that contain kiloohms. In fact, when you're doing electronics and things, your resistances usually are kiloohms. Ohms, 2, 3, 4 ohms, are actually really, really unusual resistances because the current going through them is too large, and it tends to get the things far too hot. So we tend to use kiloohms quite a lot. You could have megaohms, you can have milliohms, same as all other SI units. Okay, quick look at the examples for the maths. What's the potential difference across a 20 ohm resistor if there is 0.3 of an amp flowing? Well, we write down Ohm's law. I've got a pen here. Write down Ohm's law. V equals IR. And I is 0.3 and R is 20. Therefore, our answer is 6 volts. Looks like there's only one significant figure, so 6 is correct. Okay, very straightforward. What is the potential difference across a 1.5 kilo ohm resistor if there are 0.06 of an amp flowing? So slightly harder. V equals IR. Now I is 0.06 and 1.5 kilo ohms. So kilo means times 1,000, so that's 1,500. So I reckon that comes out to be 90 volts. I haven't got a calculator in hand, but I'm pretty sure that turns out to be 615s 90. What's the resistance of a resistor measured to have 0.2 amps flowing through it for a PD of 18 volts? Okay, so again, V equals IR. But this time we want to find R. That means we need R to be the subject of our formula. To get something on its own, you have to shift whatever things are with it to the other side of the equal sign, and when you take them to the other side, you do the opposite. So the opposite of multiplying the current is divided by the current, so voltage divided by the current. And so what have I got? I've got 18 divided by 2. Not very difficult. 9. And unit ohms. Now, however, I've actually slightly got that answer wrong, because if you look at the question, that bit there, that 0.0 is not necessary. The only reason that 0.0 is there is to tell us that it's intended to have 2 significant figures. This one's got 2 significant figures. My answer's only got 1 significant figure. So I've got to sort that out. So actually my answer ought to be 9.0 ohms. And that 0.0 is telling whoever looks at it that I understand that the question was to 2 significant figures, and my answer is to 2 significant figures. What's current thrown through a 120 ohm resistor measured for an applied PD of 18 volts? Okay, V equals IR. This time I want I, so to make I the subject, I've got to move R to the other side. Opposite of multiplying by R is dividing by R, so the voltage divided by the resistance. And what have I got? I've got 18 volts divided by 120. Well, 18 divided by 12 is 1.5, so therefore my answer must be 0.15 amps. Two significant figures, yeah, lovely, works perfectly, no extra thinking. Right, and then the final one of these examples, and the last thing in this little tiny presentation, is what's the resistance of a resistor in a fragment of circuit below. Now, very often when what's going on is you're solving circuits. So you're looking at the picture of the circuit and you're thinking about what's going on within that bit of that circuit. You're not doing written out questions, which are the ones we've been doing up till now. So I've just drawn out a little tiny bit of a circuit here. I've shown that the voltage that's being measured across our resistor is 8 volts. And I haven't drawn in an ammeter. I usually don't. I've just drawn in an arrow to indicate where the current is flowing and said that the current is 20. And of course, a small m means milliamps, thousandths of an amp. So I've been asked for the resistance. I know the PD. I know the current. So it shouldn't be too hard. So I write down Ohm's law. Been asked for the resistance. And here I've got 8 volts divided by 20 milliamps. So the only thing with the 20 milliamps is I've got to convert it into amps before I do the calculation. And 20 thousandths is the same as 0.02. So that looks to me like that's going to be 400 ohms. Because 2's going to 8 4 times, and then I've got 4 divided by, that's a hundredth, isn't it? So 4 divided by a hundredth will be 400. Okay, 400 ohms. Right, that's the final one. You can work out without too much thinking, I would guess, what questions I'm going to set you to go with this. I'm not going to write hundreds because they're not only tedious to do, but they're tedious to write. But I will set a few just to make sure that you've watched this and paid a little bit of attention.